Good afternoon, everybody. Welcome to our webinar about the advanced preparation methods of TEM samples. First, I'd like to thank you very much for being here because it's so nice to see the great number of the participants. It's a good feeling. Thank you for that. My name is András Szigeti. I'm the CEO of Technorglinda company. I will be your host today. And let me introduce my colleague, Dr. György Zoltán Radnóci, who will be our main presenter for today.
Good afternoon.
György is a scientist, a physicist, and also an electron microscopist who specialized for the TEM applications, which is very useful for today because he can show us some very nice examples about the TEM preparation and the result, what we can achieve, right? This is a quite famous sample. It was prepared on the Berkeley University in California in 1999. And why is it so important? First, because it was prepared with our machine, the IV4. That was the first ion mill what contained a dedicated low energy ion source on the market. And why it was so important? Because that was the very first chance to remove all those amorphous and destroyed layers caused by the mechanical preparation or even caused by the high energy argon ions, what covered this kind of detailed structure. So actually from that moment it was a new possibility which was given to the scientists to evaluate the completely amorphous and damage-free atomic structures. Basically a new era. So yeah, this is the world of TEM samples, and I will ask my colleague to continue and show us some details and nice examples how and what we can do.
Yeah, thank you, András. As András told you, I'm going to show you the way of preparing perfect or nearly perfect samples. And he also told you that I'm a researcher, so I've been the user of ion mills and related tools for now about 20 years. So let's have a look at the argon ion milling in detail. So the end result for a TEM sample should be, it should be thin, depending on the experiment type, but it should be between 5 and 500 nanometers usually. It should be mechanically stable, and the shape should be a 3 millimeter disc, which fits the sample holder of a microscope. It should be free from artifacts, and it should be clean and smooth. So that's what we need. More specifically, that's how a TEM sample looks when it's ready after ion milling. So we have a titanium disc, and the sample is embedded in the middle of the disc. There is a small hole in the middle of the sample material, and the edge of the hole will be thin enough for electron transparency. The thickness of the titanium disc after ion milling should be no less than about 20 microns and no more than 150 microns. Yeah, and that's what we need. Let me show you an example. This is an argon ion milled diamond piece, and you see on the left image how the sample looks when the ion milling is finished at 3 kilovolts with a high energy gun. So on the lower part of the image you see some lattice of the diamond, but obviously this sample cannot be used for a proper investigation. Now, if you clean this sample with 500 volt argon ions, you will notice that the lattice image looks much better. But let me show you. Oops, I need to go back one. Thanks. Where is my mouse? Yeah, there it is. So you see that there is still an amorphous band at the edge of the sample. So it indicates that we still have some amorphous material on this sample. But if you look at the right image, which shows the sample when it was cleaned with 300 volt argon ions, you only see a very, very little amorphous edge, and the lattice image here, it looks much, much better. Let me show you the next example. This is a piece of aluminium oxide. The image on the left is a raw fib cut lamella finished at 16 kilovolts, and you see that there is some lattice in it, but you're not really able to evaluate it. It's dirty. It contains a lot of amorphous artifact, so this is not what we want. The right image shows the same sample cleaned with 300 volt argon ions, and you see it's a crystal clear image.